Well, thank you all for coming. I'm excited to be here. I'm still kind of new to Chicago. I moved here last summer, so I'm excited to be kind of meeting this group for the first time. So I probably don't have to tell most of you that visualizations are increasingly common in the media as well as for analysis. And as they're used to support decision making and inform the public, I think they play this important role in kind of helping us understand what we should believe about the state of the world, whether that's climate change or, as in this case, what's going to happen in the next election. So here we're seeing predictions of vote share from a 538 model leading up to the 2016 election. So this is from a day in August 2016. And we can kind of interpret these estimates, which are based on poll data, as sort of the best prediction of what might happen if the election were run on that particular day in August. And so we might look to this data as the best possible estimate, but we have to also remember it is just an estimate. So most of the data we visualize is subject to uncertainty. So here, for instance, we can't survey the entire US population, and so there's going to be some sampling error. And if we think about how visualizations can convey that data is approximate, this visualization does, I think, an okay job in that you can see that there are kind of shaded confidence bands around the vote share for each candidate. So, at least hypothetically, a user who is paying attention to this could see that, there is some chance that Trump could have a higher vote share, according to this model, than Clinton. But I think if we think about how the visualizations that we see kind of typically in our casual encounters with data in the media and even sometimes in analysis settings, it's kind of striking how comfortable we feel presenting estimates without any acknowledgement necessarily of their fallibility or of their uncertainty. And so we have extremes like the Congressional Budget Office, which doesn't publish uncertainty with estimates even when they're talking about trillions of dollars. So we assume there's some error, some approximation there. And then we have organizations like the Pew Foundation, different data journalism outlets that are trying to be responsible with data, but are presenting visualizations of estimates. Like this example, this is a map of estimates of the number of unauthorized immigrants in different cities in the US. Where this is a hard thing to measure. There's undoubtedly some error here. But the information that Pew gives us about uncertainty is kind of buried down the page. So if we actually read the entire text article, around the middle of it, we'll see that they say things like, actually, not all of the differences that you see in this visualization are reliable or significant. But the chances that the average user is getting that information, I think, are low. We don't see it in a way that is integrated with the visual. So I've been using my work over the last few years to try to identify ways to improve visualization's ability to kind of help people understand what they should think given different data, or in other words, to kind of promote good statistical reasoning. And so I was going to talk today, kind of give an overview of projects related to kind of two themes in this this kind of goal I have. So one is related to visualizing uncertainty in a more accessible way, or a way that people can understand. And secondly, I'll talk about some work I've been doing where I'm thinking kind of about how maybe uncertainty visualization alone is not always the answer, and we have to get people to think more critically about information and think kind of beyond the data by getting them to think kind of about what do I already know that's relevant. And I feel like I should give some disclaimer. I'll probably use some stats terms, but you don't have to understand them all, and I'll try to refrain as much as I can, but you don't have to kind of understand them all, I think, to get the point of what I'm talking about. So sometimes my talks are kind of like stats class, and I don't know what to do about it. So I'll start with visualizing uncertainty. So I would argue that if we look at how we currently visualize uncertainty, we lack many effective kind of widely generalizable techniques or methods that work for different audiences. So if we look at the existing methods, we can say that most of them are either some representation that we could call summary marks, where we're using things like error bars or box plots to kind of graphically annotate properties of a distribution. Or on the other hand, we see visual variables, where we have some probability or confidence value, and we are mapping that to a visual variable. Like in a violin plot, you could say it's area. In a scatter plot like this one at the top, you could say I'm using color lightness to show probability. And then this gradient plot is using transparency or opacity. And so in all of these cases, we can assume we have some probability distribution, and we're trying to show it. But all of these different techniques also, I think, have some issues if we look at sort of standard criteria we use to evaluate visualizations. So in visualization research, we talk about expressiveness, which is basically this idea that a visualization should express the data in a way that the viewer's natural interpretations or spontaneous interpretations are correct. And so if we look at things like error bars, for instance, they tend to make people believe things, or people's spontaneous interpretations do not necessarily match what the data is actually saying. So for instance, there's this bias called within the bar bias that a lot of people have when they look at error bars, where they think when they see a bar chart with an error bar that the bottom half of this range is actually values that are more probable. In reality, that is not true. Another problem is, even if we're not seeing this within the bar bias, error bars can be used to show many different statistical properties like standard deviation, standard error, confidence intervals, and they look the same every time. And if you don't sort of suffer from within the bar bias, you might think, oh, this is a uniform probability range. Any of these values is equally likely, because that's what it looks like. But in reality, that's only true for certain meanings of error bars. So if you have a 95% confidence interval, it is in fact a uniform probability range, but no one really understands what a 95% confidence interval actually is because it's itself incredibly confusing. So we have different ways in which error bars and these other graphical annotations kind of lead us to think things that are not actually true about the data. On the other hand, if we look at these visual variables, they kind of don't do so well on another criteria we use to evaluate visualizations called effectiveness. So effectiveness is this idea that you want to visualize data in ways that kind of maximize the viewer's ability to actually read those values back. So in visualization research, we look a lot to the results of graphical perception studies, where people have actually had people make different types of judgments, like judging proportion, et cetera, from many different visual encodings, things like position, length, area, color, et cetera. And we can rank how well people can do these kind of sort of data reading tasks from different visualizations. The problem with visual variables being used to show things like probability is that often we're already using the best visual encodings, like position in our scatter plot, or in one of these plots where the y-axis is being used to show some actual data value. And so then we're left, when we're trying to show uncertainty, with these kind of less optimal encodings that people can't actually read very well. And things like blur, for instance, which people often think, oh, it looks like uncertainty, it seems to make sense, are extremely hard for people to quantify. So people look at different shades of blur and they can maybe see a difference, but they could not tell you how big that difference is. So kind of going against the point of visualizing data in the first place. So when I started thinking about this problem of how do we develop visualizations that kind of better help people reason about uncertainty that don't have some of these issues, I really started by kind of wondering, well, how do people naturally think about probability? So even before we start thinking about visualization, like what helps people reason about uncertainty? And so I found in the cognitive psychology research that there's actually this robust finding that if you want people to better understand probability and do better on things like classic Bayesian reasoning tasks, you can simply reframe it as a frequency. So rather than saying 30%, I might say 3 out of 10 times this is going to happen. And one of the potential reasons that people better understand probability as frequency is that if you think about how we experience probability or uncertainty in our lives, there are events that we witness. So things like maybe I get to the bus stop every day at the same time, and I want to kind of estimate, what's the probability I'm going to catch the bus. And the way that my mind does that, or the way that I experience that in the world, is as a frequency. So I might think, well, 4 out of 5 times a week when I get to the bus stop at this time, I do in fact catch the bus. And so what I wanted to do when I started thinking about uncertainty visualization is find ways to take this frequency framing and kind of use it in visualizations that show probability distributions or that show uncertainty. And so to take a particular context, we started thinking about people using transit applications, things like this one. This is One Bus Away, which is used in a variety of cities. I don't think in Chicago, but Chicago has similar apps where people use these things to look at, to get estimates of when, for instance, their bus is going to arrive, and they make decisions like when should I leave to get to the bus stop given these predictions. And this is a case where people who use these apps, I think, are pretty aware that these estimates are not deterministic, so there is some uncertainty. So if you've ever used one of these apps, you've probably been in situations where it told you your bus was going to be here in 5 minutes, but your bus actually came in 4 minutes and you missed it. So this is a case where we could imagine showing uncertainty, but we would want to do so in a way that people actually could grasp what it meant, regardless of their statistical background. And so you can imagine for any one of these estimates, like this is the bus is going to come in 2 minutes, we actually have a probability distribution based on the historical bus data or the GPS that we're getting for the bus. And we want to make a visualization of this distribution that uses this kind of frequency framing. So rather than this continuous kind of function, we want to show something where there's different dots representing the probability of buses coming at different times. And so a naive way to do this would just be to take our distribution and draw some number of samples from that distribution, say 25 or 50. But what happens is that we get these kind of noisy looking distributions if we just randomly sample. Unless we have a huge number of dots, like 1,000 dots maybe, we'd get something that looked pretty perfectly like this. But then the frequency framing is maybe not so useful anymore because it's basically going to converge to just an area estimate anyway. So what we wanted to do was create a way of making these kind of discrete framed visualizations of uncertainty where we could use any number of dots and it would still look kind of representative. And so what we did was come up with a technique called quantile dot plots. The gist of it is that we're going to look at the distribution function and sample proportionally to the quantiles so that even when we have a small number of dots, say 20 dots, we still get something that's a pretty representative approximation of what we're trying to show. The kind of thing that we liked about this is that going into this research, we weren't really sure how many dots should we use to make a distribution like this. So for instance, because we're drawing samples, there's still some kind of precision lost every time we reduce the number of dots. So 100 dots is going to be more precise than 20 dots. But at the same time, we thought that there might be benefits of fewer dots, in particular because the visual system is capable of doing this thing called subitizing, which means that we can look at a small number of objects and immediately recognize how many things we're seeing. And so it usually applies to things that about the number 4 or less of items. But it means that you don't even have to count or think. You just kind of know. And so in particular, we thought for this bus context, because people probably often care about one-sided intervals, like if I get to the bus stop in 8 minutes, how likely is it that I'm going to miss the bus? We thought that smaller number of dots might be good. But we wanted to study this, and so we did a few studies. So we first had bus riders in Seattle, about 500 people, use a variety of displays, and we just looked at how well could they read the probabilities. So how well could they kind of get the information from the plots. And we found that the dot plots with 20 dots did really well there against a variety of other kind of non-discrete or non-frequency visualizations. We then did a second study where we actually wanted to look at kind of does this help people make better decisions. So we had a number of visualizations we wanted to test where we had people in this case actually look at a display and make a decision about when to leave for the bus, and then we kind of scored their decision. So here we included dot plots with 20 and 50 dots. We also included things like intervals, which everybody sort of naturally associates with uncertainty, even if they don't understand them, density plots, text, because some people think uncertainty is already overwhelming, so text is kind of an easier way to give it. So we would give them the most likely arrival time of the bus, but also a one-sided interval, like a 60% chance that the bus will come in this many minutes or later. So we varied that. And then finally, I think in a lot of times when you're debating visualizing uncertainty, there's this question that comes up of like, is it actually going to help people at all? Because it's complicated, et cetera. And so we also had a condition where we didn't have any uncertainty, just to see, like, do bus riders, as they're making these decisions, really need to see uncertainty? So we did a study where we had people use these different displays. They made many different decisions. And for each decision, we kind of set it up like an actual kind of busing scenario. So we had realistic incentives where you would be rewarded more for catching the bus. You would be rewarded even more if you caught the bus on a day when you needed to get to an important meeting. And you would be penalized for things like waiting at the bus stop for a long time, especially if it was raining. So we tried to make this realistic. And then what we could do based on the data was actually score kind of how good were people's decisions. And so these are just plots of results. Oops, it's kind of blocking the text, but I think you get the gist. So here we're just seeing the decision quality. This is basically comparing their decision to the best possible decision they could have made. So up is better. And then each of these plots is showing results or model predictions across 40 different trials. And so between each decision people made, they got feedback on how they did, so they could actually learn how to do better. And so we wanted to kind of see first, like, which visualizations helped people make good decisions right from the start, and then which visualizations help people kind of correct their behavior most quickly, et cetera. And then the sort of width of these gray bars is just how consistent people were in making decisions of that quality. And so one thing we see is that the dot plots do well. Another thing that did well that kind of surprised us was a cumulative distribution function. Most people, I think, or previous research has shown that people have trouble understanding these, but I think because this task calls for a one-sided interval, this was actually the right kind of representation, so maybe wouldn't transfer to other contexts. Another thing we saw was that in this case, uncertainty seemed to help people in general. So no uncertainty, there's a lot of variance. People start off pretty bad and they don't improve much, as we might expect. The only case that really seemed to do worse than no uncertainty at all was one of the text intervals. And so with the text, we saw that the kind of performance was sort of varied depending on what interval we gave people. So 85% confidence interval maybe doesn't make sense to people. We don't have a good grasp of 85%, whereas some of the others, like a 99% confidence interval, people seem to do better with. So text was kind of all over the place. But in general, kind of the dot plots were less variance and started better, ended better. So we thought that was promising. And I think one of the reasons quantile dot plots or these frequency-based visualizations can help is that it's kind of immediately recognizable what you're seeing, or the fact that probability actually can be thought of as a frequency. But unfortunately, there's also, I think, situations where showing a static plot of a distribution, even if it's a quantile dot plot type plot, is not going to help people. And that's because we know that people sometimes like to ignore uncertainty. So sometimes people are motivated to kind of just want a certain outcome to happen. And if they see uncertainty, they'll ignore it. So for instance, you can imagine these are political candidates. I'm showing you data on kind of who's going to win again. You want the blue candidate to win. And so what we've seen in studies is that in situations like this, people might, when asked kind of what's the probability that the blue candidate will win, will just kind of answer based on which one has a higher mode or a higher mean. And so there's kind of a lot of evidence in judgment and decision making that people like to kind of ignore uncertainty. And unfortunately, when you have the whole distribution shown at once, you can do things like focus on the mode and just kind of ignore the variance. And so one of the things that I started thinking about related to this is kind of that we almost need to force people to look at uncertainty in certain cases. Another kind of issue besides people ignoring it is that these displays don't allow you to answer certain questions. So if I actually asked people what is the probability that blue wins, they might say, well, blue is going to win, but I think they'd have a really hard time making that probability estimate because these displays just don't show the information in a way that we can kind of make these multivariate comparisons. So I was starting to think about kind of how could we design displays that don't allow people to discount uncertainty and that can answer questions like this. And one thing that we can do is kind of similar to something that's like a frequency-based representation of the whole distribution, but where we're only going to show one draw or one of these samples at once. So I call this hypothetical outcome plots. So here, I mean, we're seeing them as lines, but we're basically just taking random draws from each of these distributions, showing one at a time as a frame in an animated visualization. And you'll notice that it's now very hard to ignore the uncertainty. You basically can't ignore it because there's not kind of a central tendency for you to focus on. And so this is a very different way of visualizing uncertainty, but there's actually research in perceptual psychology that kind of motivates this. People are actually surprisingly good at estimating distributional properties. So for instance, relatively like how frequently they saw some event happen as they watch kind of these animated displays. So we did some studies originally looking at how well can people perceive properties of a single distribution. So if I asked you what do you think is the mode, or what do you think is the probability that the value is above some threshold, people did approximately as well from these moving hypothetical outcome plots as they did from things like violin plots. So that was kind of surprising to us. But what we were also interested in is how much better they could estimate things like the probability that blue wins from something like this, because it's actually showing you information that directly conveys that, whereas it would be very hard here to get that information without kind of knowing the statistical theory. So they're very different, and people, I think, initially are kind of freaked out when graphs move. But there's other reasons as well. So besides kind of better supporting kind of comparisons or multivariate probability, there's lots of cases where you might have a complex visualization already, and to think about like how am I going to put an error bar on it is difficult. So a choropleth map, for instance, it's very hard to show uncertainty. However, if it's not already animated, you can always basically simulate other possible values of your data, and there's lots of techniques and statistics that are actually surprisingly easy to use to do this. And then you can show uncertainty regardless of how complex the visualization is. So we did studies, like I said, looking at kind of how well people could read the data back or read probabilities. But we've also done some studies looking again at kind of more applied decision tasks. So one that we did was kind of motivated by the way journalists, like at 538, have used these animated hypothetical outcome plots. So they did, for instance, a piece where I think my animation is not working. There it goes. To help people understand uncertainty in the jobs report, which is just this set of monthly estimates on how many jobs were added to the economy. Journalists often will interpret the jobs report as meaning, you know, like the economy is really growing or it's not. And so they wanted to show that even when you had zero growth based on sampling error, the fact that we're not actually measuring every single job, you could see things that looked like a trend, and conversely, even if there was a growth trend based on sampling error, you could see things that look more ambiguous. So what we wanted to do was basically take a task inspired by this. So the idea of the task would be, we're going to show you some jobs numbers, and you're going to tell us, is there a growth trend or is there not? And we wanted to have people do a lot of these judgments where we varied how we showed them the uncertainty in the actual kind of trends to see, you know, do these hypothetical outcome plots that the Times had used actually help people do this kind of task better. So we had a bunch of these different jobs numbers. So each person in our study did a lot of these different trials where they would use two different visualizations. One would be the hypothetical outcome plots, the animated plots, and one would be some static representation of uncertainty like error bars. There's the hypothetical outcome plots. We also did things that were still had kind of a frequency framing where you could see that probability actually means like all these different outcomes, just to see kind of how do the hypothetical outcome plots compare to something where you are kind of getting some frequency framing, it's just static. And so what we wanted to do is really see, could people make judgments that were kind of more difficult using one of these different displays over another. And so we needed a way to kind of measure for any given set of numbers that we showed someone, how difficult is it to tell whether there's a growth trend or not. And so for that, we can basically look at, it's basically a ratio of probabilities that it came from the growth model versus the no growth. So all of these on the top row came from or are more likely to have come from a growth model. But on the left side, they're kind of difficult. It's hard to tell. And then on the right side, they get easier. And so we could basically have people make many of these different judgments where sometimes they used a static representation like error bars. Sometimes they used hypothetical outcome plots. And we looked at kind of how accurate they were. One thing that we found in this data, because we had everybody using multiple visualizations, we could see kind of on average like which visualizations help users do best. And one of the things that was kind of striking is that nearly every single person in our study did better with hypothetical outcome plots than with a static representation. And so this kind of means that, or one way to think of this is that when people using a static plot were basically making a random guess, like in these two examples, people using a static plot, their accuracy was about 50%, so you're basically just guessing. People who used hops for these same stimuli were about 75% or more accurate. So people were able to make these judgments from kind of less underlying information. Another interesting thing was that we had everybody do kind of blocks of trials where they used hops and then they used error bars or vice versa. And people who used hops first did better with the other visualization. So it's almost like there was this learning or effect or kind of an effect on how well they could kind of internally represent uncertainty in this task. So even with kind of a worse representation of uncertainty, they still did better because they had used the hops before. So this was also kind of interesting, and just a couple examples, I think, of how a frequency framing for uncertainty visualization or for showing probability can be useful. So my advice kind of to those of you visualizing uncertainty would be, when you need a static plot, use quantile dot plots. Smaller numbers of dots, I think, are a good idea. But if you can do animation and you're worried that people might ignore uncertainty, and uncertainty is kind of important to the decision, then I would use hypothetical outcome plots. And you can do this regardless of your visualization. The stuff to look for in the statistics lit would be something called bootstrapping, which is just a way to resample your data. I didn't talk about it, but we've also done studies to look at things like, how fast should they move, or should you use animated transitions? And in general, about a couple frames per second or 400 milliseconds per frame works well. Animated transitions, I think I have an example, actually, I think make it harder. So here's an animated transition, so it's kind of interpolating between frames. And this made it worse for people. So people it looks nicer. People don't like when it's so jumpy, but it actually, what you want people to think is like random samples. And so when you interpolate between them, people start to see connections between them. Okay, so I think there's hope for visualizing uncertainty in ways that people can better understand. And a lot of these studies I showed were done on lay people or bus riders, et cetera, so not scientists. But at the same time, a couple years ago, I started thinking that maybe better techniques for visualizing uncertainty are not going to solve the problem of not enough presentation of error when we show data. And so I think recently, in particular, I've been talking to different visualization authors, trying to understand kind of what are some of the reasons that we might decide not to show uncertainty, not to add error bars, et cetera, to visualizations. There's also been prior work on this, talking to people like at government agencies who are regularly presenting data and asking, why don't you communicate uncertainty more often? And there's a lot of rationales, I think, that authors have, some of which are hard to argue with. So, uncertainty is cognitively kind of effortful to think about for users. You don't want to kind of push that on your users. There's fears that users won't understand it. There's fears that, as an author, I'm not totally confident in how I quantified uncertainty, and users might kind of take that as really precise uncertainty information, and I don't want that, et cetera. So I think it's a really hard problem, and one that I'm probably going to be working on for a while, kind of figuring out how do we actually get people to feel more comfortable presenting error. And so as part of kind of realizing that this is a bigger problem, one of the things I started thinking about is kind of how can we make people more critical or think more critically about data or think beyond data even without just visualizing uncertainty. And so one of the ways I've been thinking about that is that we could get people to think about what they already know that might be relevant as a way to kind of prompt kind of more critical thinking. And even begin to do things like evaluate how well they're listening to the data, even when we're not showing uncertainty at all. And so to give you kind of a sense of the motivation behind this idea of prior knowledge when we look at graphs, I started thinking back as a PhD student actually about this idea of visualization interpretation as kind of a process where we're implicitly or kind of mentally imagining something, some pattern that we're looking for, and we're comparing the data that we see to this imagined model or reference. So for example, if I show you a histogram like this, most of you are probably kind of implicitly imagining some sort of bell curve and comparing the distribution to that, because that's what we're used to doing with histograms. If I showed you a line chart, you might be imagining a diagonal line representing a perfect linear relationship and kind of comparing the data to that. And of course, what you compare to is going to shift maybe based on how I show you the data. So especially if I'm showing you something like a histogram, then you're going to want to imagine a bell curve. But also, it's going to matter what the data represents. So if you told me that this data was, say, the amount of time I have between meetings, then my expectation of what it should look like might shift, where now I think, oh, it should be more kind of probability mass over in this negative because I'm usually late. So there's all these factors that kind of influence what we might expect to see in data. And so I wanted to start thinking about how do we get people to actually make these kind of expectations or predictions explicit. And so with an interactive visualization, you can just kind of have people draw what they expect to see, and that's a way of kind of getting them to articulate their expectations. So you can imagine I'm a journalist, and I'm going to show you some data, maybe again, model predictions. This time I've taken poll results from Chicago, and I'm trying to predict the percentage of voters in Chicago who will vote Democratic in 2020. And so before I show you the data, which is what I would normally do if I was a journalist, you would just see the data right off the bat. Instead, I'm going to ask you to first sketch your prediction. So think about across these different income levels that I've set up on the axes, what you think this percentage of voters will be. So if you do this kind of prediction and actually take the time to think about it, I'm guessing that now when I show you the actual data, which is fake data, but pretend this is real, it's going to be hard for you not to want to compare your predictions to what you're seeing, just because we like to know kind of how did I do. And so originally when I started thinking about this work or this idea, we started doing experiments just to see like what is the effect on the user of having to make a prediction and then seeing the data kind of against your prediction. And so we did some sort of quasi-psychology studies where we had people do things like draw their predictions in a graph. Some people did not draw their predictions. Some people did other kind of like reflection activities, like they had to explain the data to themselves, but they didn't predict. And then we looked at kind of how well people remembered the data better later, which in psychology is often used as a measure of kind of comprehension. And what we found was that when people made a prediction and then saw their prediction against the data, that was enough to help them remember the data better later by about 20 to 25%. And that was equivalent to some of these other more complicated educational psych techniques, like writing yourself an explanation of what you think the data means. Another thing that was interesting is that we tested this for various different data sets, and we intentionally varied kind of how familiar we thought the data sets would be to people. So we had some really obscure data sets like scientific experiment results where we thought people cannot possibly have good prior knowledge about this just because no one does. And we found that people still remembered the data better later if they made a prediction, even when their prediction was basically kind of meaningless, like they just made it up on the spot. So it appears there's kind of these individual level kind of benefits, maybe rhetorical benefits of having to do this kind of thing. We also were interested in how seeing other people's predictions can change your own ability to remember data. So even if I haven't made a prediction, if you show me what other people said or thought for this data, does that help me somehow focus more on the data and remember it? And we found that it did. So similar amounts of kind of improvement in recall just from seeing other people's predictions. And then we also wanted to start looking at like what do people actually believe later? So it's one thing to ask them to just recall the data, but often what we care about in visualization is kind of, are they actually sort of listening to the data? And so we also asked them in this study, they made their initial prediction, or some of them did. We showed them data, and then we asked them, now what do you believe after seeing the data? And we found that what you predict beforehand, not surprisingly, influences what you believe after seeing the data. And what other people believe can also influence kind of how you update your beliefs or how much you listen to the data. So if you disagree with the data and everybody else disagrees with the data, then you're not going to take the data as seriously. So again, kind of interesting effects on individuals, potentially better memory for data, potentially kind of social engagement if you're showing people predictions. And the New York Times has actually made some visualizations. They call it You Draw It. Where they have users basically make a prediction and then they show you what other people thought. And so I think they're kind of aware that there's something kind of engaging about this kind of thing. But they've only made a few of these. And they're kind of a pain to create because you have to create an interactive visualization that's going to work for everybody so they can kind of sketch and then show them everybody else's beliefs. And so one thing that we've been doing recently in my lab is making an authoring tool that makes it easy to create these sort of things, at least for line graphs or for time series data. So we call it They Draw It, kind of based on the New York Times, You Draw It. And particularly we're targeting journalists just because journalists, I think often, some of them at least, don't have as much programming experience, but they want to be reporting more on data, at least the students that I teach. And so this is a tool that's kind of a full graphical user interface. You come with some data, some time series data, that's something you would show in a line chart. You can tell the tool kind of which lines do I want to show by default, which ones should the user predict. You can do things like decide, do I want to show everybody else's predictions after the user has made their own prediction? How do I want to do that? And then it'll generate an iframe that you can put in your HTML, and then your users will be shown some data, maybe no data if you decide not to show anything by default. They'll have to make a prediction. They say, I'm done, and then they'll see everybody else's prediction. If you configure that, they'll see the actual data as well. So we wanted to make this easier. And there's a few kind of goals I think we had in creating this. So one, kind of see when do authors want to do this kind of thing? So for what types of data does this seem like a place to kind of ask users for a little more information about what they're thinking? And also, we kind of want to have access to people's predictions so we can look at things like where do audiences of at least like data journalism pieces have good intuitions or good mental models of kind of what the data is going to look like, and where do they have bad intuitions? Because then as a journalist, you could potentially try to inform people where you see that they're kind of misinterpreting things or having trouble. So this tool, whoops, my URL is not showing. It's called They Draw It, so you can find it, and this is in collaboration with the Knight Lab, which is a computational journalism lab down at Northwestern, where I am faculty. So check it out if you're interested. I want to just spend the last few minutes talking about what else kind of inspires this idea of creating interfaces that will allow people to sort of articulate their prior beliefs. From a research perspective, there's some really interesting things we could do as well. So we can see, what kind of data they want to do this with, what people's predictions look like. But it would also, I think, be helpful if we could actually evaluate how well is someone sort of listening to the data, given what they believed beforehand. When we show them the data, kind of how much are they actually listening? Do they appear to be acting rationally in terms of how they update their beliefs? And I think this gets back to this goal of visualizations, where ultimately we kind of want people to pay attention to the data, use it to inform their actions, but we don't really want them to kind of overwrite everything they know if they have useful prior knowledge every time they see a new data set. That's not really how comprehension should work. And we also don't want them to disregard the data completely. So there's this notion of like there's an appropriate amount of weight to put on a given data set, and you should weight the data or pay attention to the data proportional to kind of how much information it contains or how certain it is. So to kind of give an intuition for this, going back to this example where I'm going to show you predictions of the percentage of voters voting Democratic in Chicago in 2020, you can imagine that you make your prediction, and then I show you some data, and I tell you that actually this is a really small sample. So I asked like 40 people in Chicago who they're going to vote for, and that's what this data is showing. And imagine that you've seen prior polls, and so your prediction actually represents more information than my sample does. So maybe in terms of what you believe after looking at the visualization, you kind of want to stick with what you already knew. Like you got a little bit of more information from this data set, but there were only 40 people. So it's not really going to shift your views, provided you'd seen other results before this. On the other hand, if I told you that I polled 700,000 people in Chicago, and for context, 900,000 people or approximately voted in the last presidential election, then you should really pay attention to this data. Even if you thought you knew a lot going in, I've now told you basically at this point of time, the best possible estimate of what people are going to do, assuming you believe poll results. And so I would expect you to update your beliefs or to later kind of believe something that's pretty close to my data, assuming you think my data is accurate. And so this is kind of what I mean by sort of evaluating how well people update their beliefs. And so what we've been doing, which I won't go into great detail about, but which allows us to kind of make these evaluations, is using Bayesian inference, kind of a statistical approach where we can actually predict kind of what a rational person would believe after we showed them the data, given the prior beliefs that they had. And so in Bayesian inference, basically, you assume that someone has some prior information, like you have information you've gained from looking at previous data, et cetera. You have some data set, and now you want to update your beliefs proportional to kind of the amount of information in this new data. So we can basically make these predictions using this Bayesian process. The main thing that we have to do is that we can't just ask someone to just kind of in a line chart sketch a single line. What we need for Bayesian inference is to get a sense not just of what they predict, but how certain they are about their prediction. And so we have to think now about things like, how do we get them to maybe adjust an interval around their best prediction, or have them make multiple predictions? So maybe I ask you, tell me a couple different things you think that would be plausible for this trend. And then I can kind of treat it as a distribution. Of course, I've just been showing line charts, but our goal is to kind of do this for all sorts of visualizations. So we've been kind of thinking about, given different types of visualizations and types of data, how would you elicit someone's predictions in a way that kind of seems natural? So we've made interfaces and done some studies on things like having people predict a distribution after seeing a scientific experiment reported. But I think there's also kind of if we can figure out kind of how to elicit predictions and how to model them in a Bayesian way, there's these interesting applications, which I think you could call kind of Bayesian interaction design, where maybe if we know your prior beliefs and we know how certain you are, we could actually change how the visualization appears in a way that makes you kind of more likely to pay attention to the important information in it. I think there's interesting questions about, like, maybe if we're not visualizing uncertainty, we can ask you for your own kind of sense of uncertainty around the data we're going to show you, and maybe that could function almost as a form of uncertainty visualization, but without ever visualizing it. We can also do things like have you think about uncertainty in your beliefs, and then maybe we show you the data and we give you a little bit of extra information, like the data is this many times more certain than you are. So all of these things are possible if we kind of analyze interpretation as like a Bayesian process. So kind of point here is that there's lots of exciting, weird things we can do that I think could actually improve how well we sort of think about how our users use the visualizations we show them. So I will end there. Just to close, I think hopefully I've gotten you interested in what an uncertainty-aware paradigm for data visualization might look like. Frequency-based representations, I think, work well in a lot of cases, especially for users that don't have statistical backgrounds. And then, I encourage you to check out this tool that we built and start thinking about how do you get your users to actually think about what they know, rather than sort of treating each new data set as like the ultimate truth. So thanks for coming, and thanks for your attention. Are there questions or no? Okay.
Approximately 10 minutes for questions. Nick has a mic, so if you have a question, put your hand up and he'll bring it to you.
Over here?
What do we got?
I can just give, I saw this one first. Do you mind?
Okay. Thanks a lot. So you talk about the users, right? And do you differentiate between different users groups and between their prior knowledge and how that impacts the results?
A little bit. A lot of the stuff I've shown today is lay people, so not necessarily scientists. We have done stuff with researchers as well. I don't really differentiate a lot when I talk, in part because the results are usually pretty similar. So I think one of the things that I think certain people find so surprising, but if you look at like the research and judgment and decision making, is that a lot of these biases towards kind of discounting uncertainty, et cetera, kind of appear across the board in experts and lay people. But most of what I presented today were lay audiences, and like I said, I think it's likely to help as well with the experts, and what we've seen in the studies we have done with researchers have shown similar results. But that's a great question, and I think one of the things we're interested in is in looking at how people update their beliefs. Whether certain people are consistent in how they update, even if they don't do it well, like kind of figuring out if there's different types there, I think could really be important. So in general, I don't like to lump everybody together because that's, I think, sometimes unrealistic. So thank you.
I have a question about, it's kind of related, but apart from like experts versus non-experts, have you identified any kind of personality or psychological traits that lend themselves well to interpreting uncertainty?
Not really, no. That's an interesting question. I think a lot of the aversion to uncertainty is pretty much across the board. I know there's like psychological studies of how certain people don't, based on parts of their brain being damaged, they no longer try to suppress uncertainty, or they can deal with it in different ways, but I haven't looked at it too much. In general, we see some differences. There are certainly differences in terms of how much attention people are willing to pay to read a description, but I would say that's as far as kind of personality differences go. But yeah, I think a lot of work in uncertainty visualization is still pretty early, so I think there's a lot of questions that we just haven't gotten to yet. So, yeah.
So I'm a big fan of doing the whole prediction thing first and then learning from the data. I come from a stats and a math background, so that's how I learned.
Statisticians usually like it.
Yeah. That's how I learned to think about probability. But one interesting thing, I also work a lot with survey research and things like that. And I do know that there is diminishing returns to how many survey questions you can ask somebody, right? Because the cognitive load and all sorts of things. Do do you find similar, or have you like looked into it at all? Are there diminishing returns from like getting people to make these predictions?
Yeah, we haven't tried to do it in or studied it in a context where people would be doing this over and over. So I think like data journalism has been one application area I've thought about where I think you would probably, as a journalist, if you were like working for an organization that was going to do this, you would still want to be a little choosy about when you did it. I do like the idea of like data journalists being able to sort of have information on kind of what your beliefs were at different times. Maybe some people find that scary, but I think we could, do a better job of presenting data if we had some kind of repeated measurements. But I agree that it's kind of a lot to ask of users, and so I have not thought about it as something that you would do every time, more like you would probably choose your battles. So that's a good question.
Yeah, so I'm interested in how behavior has changed on the part of people. And can I take away from this when you had the DATs, the predictive DATs, and then how the other people answered? Does that reinforce people's belief? For example, if I was asked the question, is this neighborhood going to improve over the next 5 years? And I answered yes. But I saw that 90% of the people answered yes. Yeah. That's right. Going to reinforce.
Yeah, so we definitely saw potential for social influence. And in some cases, you could say the social influence was kind of a good thing in that like it could cause people to question data more than they would if they didn't see anybody else's beliefs. Like it got people thinking, I think, that like data is this kind of socially constructed thing. Like it's okay to have opinions about it. The data is not perfect. But we definitely saw cases where the social influence could potentially be negative. So other people maybe had bad predictions, but they agreed with your prediction, and so you just discarded or rejected the data more or took it less seriously. So in general, I think social influence, whenever you're showing what other people thought, is always kind of a danger.
A danger to?
I mean, if it's a case where there is some true answer, it's potentially a danger to what you believe being a little bit like inaccurate based on what other people believe. So I've done works that's a little bit more direct at answering that question. So if you're having people do these tasks where there's a very clear true answer, like judge a proportion in a bar chart, if you show them what other people said, you can lead them to be wrong, even on these very basic visual judgment tasks where like you should be able to just know the answer by looking at it. So I mean, I think people are if they think they can be more correct by listening to others, they will try to be, even if it leads them kind of astray. So yeah, I think social influence is something we just have to be aware of when we're showing predictions. I think some of the reasons for presenting predictions outweigh kind of some of those, but I think it has to also be kind of on a case-by-case basis, because there might be cases where you really, if people have bad intuitions, you really don't want the average user who doesn't have a lot of, prior knowledge on that kind of believing what other people say. So I think topics like climate change maybe would be kind of contentious, where you want to be a little careful to sort of make clear that this data is actually more important than so-and-so's opinion, who hasn't looked at the data. So it's just, I think, a complex topic related just to beliefs in general. But yes.
We have a few more minutes for questions. Are there any others?
Another? Okay. Yeah.
Yes, going back to one of the first things you said about the simple dot plot, just 20 dots. So how does, if I were to make that, if I would want to project the same clarity but uncertainty and try to use their technique for just basic business data, how would I approach picking 20 dots or picking this plot?
So you're asking kind of about constructing them, or?
Constructed in a way that would actually accomplish what you accomplished.
Yeah, so so it's an actual kind of algorithm, you can think of it as, and so we, like there's an actual formula you can use. You want to sample from the quantiles, but we've also created code like in R where you could do this. So if you're using something like R, you could just use a ready-made code, but otherwise, the paper, I can point you to the paper where we discuss it about how you would do it. It's a little complicated, like you have to be comfortable sampling from theoretical distributions, but it's not like horribly complicated. It really depends on kind of how comfortable you are with stats. The animated versions, I would say, are easier to create because one thing that you can always do is take your data set and sample from the actual data you have, and that's called non-parametric bootstrapping, and it will create kind of alternative versions of your data that you plausibly might have seen, assuming you're sampling from the same distribution your data came from. So that's slightly easier in that you're not looking at necessarily a theoretical distribution. But this is getting into the statistical details, but thanks for the question.
Maybe like one more?
Oh, yeah, I can give you this one.
One of the other examples you had was a map. Could you say a few words about how this would apply in a spatial context?
Yeah, so I think I had a map of, that was actually in the New York Times, and it was like, so do you mean, when you say apply, do you mean the prediction stuff or the visualizing uncertainty stuff?
Visualizing uncertainty.
Oh, okay.
You know, because you mentioned other examples.
Yeah. So for visualizing uncertainty, we've done work with the animated presentation of outcomes for maps, just because it is so hard to show uncertainty for a choropleth map. And so if you're seeing a choropleth map of like, you know, predictions of who's gonna, or what the vote share is gonna be, like a lot of times we're seeing a single value plotted to the color of each state in a map, where theoretically you probably have a distribution under that, and you're just showing like the mean of the prediction. And so whenever you're doing that, you can just sample from each state and or each region, and you see, you know, the map kind of animating, and it's showing you, you know, possible realizations. And that's nice because even if the different states have correlations in their distributions, the visualization will show you that, which is really hard to do with a static plot. In terms of eliciting people's predictions with maps, choropleth maps, I think that's one of the harder cases, but what we've been playing with is you kind of like, you have some, I think I had a slide on it. You have some map, and you have certain areas that you want to gather a prediction from. I think doing the whole map would be a little tedious, but there it is. But you basically, we've thought about letting people basically like pick a color on a legend and then brush it on there. So, you know, I think that's one of the harder cases to elicit predictions, but I do think it's possible. So I just wouldn't want to have someone like pick a color for every single state in the US. I think that would be too much. So, yeah.
Hey, I'm curious if you've explored this type of work with personal data, and if so, if you've experienced disbelief because the data didn't reflect how highly that person thought of themselves.
Yeah, that's interesting. I haven't done much with personal informatics, but I have friends who research that, and I think, I mean, it's an area that I've been wanting to get into more, because I think there is, it's really important in certain cases where people are like tracking their weight or like trying to track, you know, their fitness, where there's going to be uncertainty, and people, I think, tend to fixate on every single little fluctuation, you know, of a scale or whatever. And so I think that would be a great application area. I personally haven't, though. And then, yes, like you said, you probably have motivated reasoning too, where you want to believe certain things about yourself. So I think it'd be a great area. Thanks.
Awesome. Thank you
Cool.
so much.
Yeah, thanks, you guys.